So for our next speaker, we're delighted to welcome Clayton Scott from University of Michigan. Clay is a professor of electrical engineering and statistics at the University of Michigan. His research was recognized by several awards, including the Career Award. And he'll be telling us about labeled noise and how ignorance is bliss today. Thank you.
All right. Thank you. Thanks for the introduction. Thanks to the organizers for this workshop. I'm very excited to be here. This work is that I'm going to be talking about has been led primarily by Yilun Zhu, who's here, and we'll have a poster this afternoon that goes into some more detail. So the upshot is I want to give a domain adaptation perspective on the problem of classification with noisy labels. All right, so let me motivate that with one slide. And let's just consider as an example the well-known ImageNet data set. This is a very large image data set where there was a lot of effort taken over a lot of years to obtain highly accurate labels for millions of images. And in particular, the creators of the data set got multiple human annotators per image to provide images, and using, then trying to find enough annotators per image to develop a consensus to get the accurate label for each image. So this is a very big undertaking. And despite all of the effort that went into creating this data set, there have been recent analyses that argue that in the test data, for example, up to 6% of the labels are actually inaccurate. So it just goes to show that even with a lot of effort, it can be very challenging to obtain accurate labels in modern large-scale data sets. Of course, a lot of times you don't have these resources. So for your data set, the labels might be even worse. What do people often do in practice? They might use some heuristics to assign labels to their feature vectors. So this has spawned an entire industry where there's companies whose business is to help other companies or individuals manage the noisy labels in their data set. All right, so the overview of today is I want to give a domain adaptation perspective on this problem. And so I'm going to talk about a quantity we call the relative signal strength that characterizes the difficulty of a label noise problem. It can be thought of as a pointwise measure of transferability. And then I'm also going to show you some supporting experiments. And the take-home message is that noise ignorance is hard to beat. In other words, just ignoring the fact that your labels are noisy and treating them as accurate labels and proceeding as usual is actually a difficult approach to beat. And it may sound like a discouraging message, but in the end, we'll show it actually, in a certain sense, can lead to really good performance. Okay, so to begin, let me just set a little notation and talk about standard binary classification. Later, I'll be extending to multiclass, but for now, let me just focus on binary classification. So this is the usual probabilistic setting. You've got your feature vector X and your label Y that are jointly distributed. And I'm going to think about that joint distribution in terms of the marginal distribution of X and then the conditional distribution of Y given X. And so a key quantity in this talk is this function eta of X. And I'm going to call that the class posterior, or just the posterior. I need to give it a name. I'm going to be referring to it frequently in this talk. And so as usual, given the joint distribution, you've got an associated risk, a Bayes risk, you've got the Bayes classifier, all standard. So this is mainly to set notation for comparison with the case of noisy labels. And my focus will be the 0-1 loss for most of the talk, although you can ask me about other losses. And in the end, I'll talk about logistic loss as well. All right, so that's standard classification. So there's a similar statistical formulation of the label noise problem that is commonly adopted in this literature, where now you have three variables that are jointly distributed, x, y, and now y tilde, which y tilde now denotes the noisy label given to x. So the idea is you don't actually get to observe y, you get to observe y tilde. And so now this joint distribution is characterized in terms of the marginal distribution of x, and then the conditional distribution of y given x. Both of those are like before. But now you have what are sometimes called the transition probabilities, the conditional distribution of y tilde given x and y. And from this joint distribution, you can look at the xy marginal, and that just defines a classification problem, just like in the previous slide. And so that associated risk, I'll call the clean risk, and then you've got the clean Bayes risk and the clean Bayes classifier. So that's basically the standard learning setting. But you've also got the marginal distribution of x and y tilde, and that's a different classification problem with its own risk, Bayes risk, and Bayes classifier. So if you see a tilde over some notation, it just means it's the noisy version of that quantity. And so here the learning problem is you get IID data from this noisy distribution. You don't get to see the true labels. Yet you still want to measure performance with respect to the clean risk. Okay, so this is again the most common formulation of classification with label noise. I'm going to take a different approach in this talk, and it's one that is really just a different perspective. It's equivalent, but I want to take a domain adaptation approach. And so before doing that, I just want to spend one slide talking about domain adaptation. Right? So you can forget about label noise for one slide. And this is just setting up the domain adaptation problem. And this is the same setup we had in the previous talk, except I'm swapping my notation for P and Q. I'm using P for the source and Q for the target. So in a domain adaptation problem, you've got a joint distribution P, and that's got its X marginal, and it's got a posterior eta P. And we get labeled data from this distribution. And then we've got a target distribution Q with its X marginal and its posterior. And there's different settings. We might get labeled data here. We might get some unlabeled data, or we might get no data whatsoever. And the goal is to, obviously design a classifier that performs well on Q. Without any assumption, of course, you can't make any real traction on this problem. So it's common to make different kinds of assumptions. For example, the covariate shift assumption assumes that the source and target posteriors are the same, but the X marginals could be different. There's another one called posterior drift, where the X marginals are the same, but the posteriors may differ. And these are illustrated at the bottom, where on the left you've got, say, a source distribution. In covariate shift, because the posterior remains unchanged, the optimal classifier remains the same as in the source, just the X marginal changes. Whereas in posterior drift, since this posterior changes, the optimal classifier may also change. All right, so now I'm going to just take this perspective and revisit label noise. All right, so we can basically think of classification with label noise and posterior drift interchangeably. That's the basic idea. So the source domain is going to be our noisy data distribution. So it's characterized by the X marginal and what I'll call the noisy posterior, eta tilde. And we get labeled data from this. That's our noisy training data. The target is the clean data distribution. And we don't get any data here, right? Yet this is where we want to measure our performance. So, you know, in a label noise problem, the clean and the noisy data have the same X marginal, so it's a posterior drift model. So this type of domain adaptation, posterior drift, it's been studied a little bit. It's not as well known as covariate shift, and so there's a smaller literature on it. But there's been a little work in trying to devise, you know, models that allow you to say something theoretically, right? Clearly, if you don't make any additional assumptions, eta tilde could be radically different from eta, and it might be very challenging to solve this problem. So people have looked at different models. One model that's been adopted is to assume that the eta and eta tilde are monotonically equivalent, and that was useful in analyzing a different performance measure. But the one I'm focused on today is just misclassification rate, right? So the most common performance measure. Focused on that performance measure, one common or one assumption that's been made in a couple of works is just to assume that the clean and noisy Bayes classifiers agree everywhere. So depicted in this figure. And there may be some applications where that's a reasonable assumption, but there's also a lot where it's not. And we'd like to develop a posterior drift model that's maybe a little more realistic across a broader class of applications. And then finally, there's some work by some of my colleagues at the University of Michigan, including Yukai Sun, who's going to be presenting here, where they drop this assumption and they make a parametric, they have a parametric model that relates the clean and noisy posteriors. So what I'd like to do is develop a model for posterior drift / label noise. I'm thinking of them equivalently. That is non-parametric and that goes beyond this assumption. It allows the clean and noisy Bayes classifiers to disagree, because that's what's going to happen in practice most commonly. Right. So that's my goal. I want to devise a class of posterior drift problems that's non-parametric and that's flexible and hopefully realistic. And so this is going to require a philosophical shift, at least with respect to the literature on the posterior drift problem. We're going to let go of consistency as a goal. And instead, we're going to accept that there's going to be some irreducible component to the error. So I'm going to pose a class of posterior drift problems where there's a component to the excess risk that can't be driven to zero. We're going to try to bound that and then try to come as close to that bound as we can and see what strategies are favorable in that setting.
Just for clarification, what you showed earlier, the Bayes decision boundary remains the same. Mm-hmm. Is that the idea?
This is in prior work. Yeah.
Okay.
Yeah.
Because even in the picture you showed earlier, the decision boundary had shifted.
Right.
Okay. So
right. So the picture shows a very general setting. Okay. This is a
trying to go towards the general setting.
Yes,
okay.
And then we're trying to go in that direction. This I would say is a more restrictive setting. And I'm trying to go something that looks much more like this figure. Yes. Thank you. All right. So how do we build up a model for posterior drift, where we're going to draw inspiration from standard classification theory. So in standard classification, how do we quantify the difficulty of a learning problem? Well, one very common approach is to look at this measure, right? The absolute value, eta of x minus a half. It's often been called the margin at x. I'm just going to call it the signal strength at x. All right, so with this notion, we've got, for example, we've got Massar's condition, which says that this signal strength is bounded away from 0 with probability 1. Or we've got a somewhat smoothed version of that, Seebekov's condition. So both of these are in terms of this quantity, which you can think of as just a pointwise measure of signal strength. How much does the label tell us about the optimal prediction at that point x? So can we do something analogous in a posterior drift or label noise setting? So I'm going to define what I'll call the relative signal strength at a point x. Suppose you have a posterior drift problem, which is defined by a triple. Got the x marginal, the clean posterior, and the noisy posterior. And let's define the relative signal strength at x to be this function, which is a maximum of 2 terms. So that first term is a ratio. And if this ratio is positive, it means the clean Bayes classifier and the noisy Bayes classifier make the same prediction. And if that's not the case, this term is negative and we'll just take 0 to be our signal strength. So in that case, in that second case, the noisy distribution at x, the noisy posterior, doesn't really tell us anything useful about the clean distribution. All right, so with this, we can then proceed really by analogy with the standard classification. We could define a Massar-like condition for posterior drift. All right, so I'm going to introduce a couple of parameters here, epsilon and kappa. And epsilon is just a probability. Kappa is a non-negative real number. And I'll define a class of posterior drift problems. Pi of epsilon kappa is the set of all posterior drift problems where the relative signal strength exceeds kappa with probability at least 1 minus epsilon. So if I was going to try to parallel Massar's condition more closely, I would just take epsilon to equal 1. 0. I would take epsilon just to be 0. But I don't want to do that because that would require the clean and noisy Bayes classifiers to agree all the time, and I don't want to do that. So I'm introducing this epsilon. And so this is the set of all posterior drift problems where, with probability at least 1 minus epsilon, this relative signal strength is at least kappa. Here's a simple illustration of these definitions. So introducing just a little more notation, A kappa, this is basically the event that has to have probability at least 1 minus epsilon from 4. Where the relative signal strength is at least kappa. And if we take kappa to be 0, we get the set A0, which is just the set where the noisy and clean Bayes classifiers agree. Here's just a simple illustration with a one-dimensional feature vector x, that's the horizontal axis, and then a vertical, the vertical axis is the posterior. And so just an example of a clean and a noisy posterior. And you can see they don't always lead to the same prediction, right? If you subtract a half, those don't always have the same sign. And okay, the colors aren't showing up on this projector. So there's, pardon? Okay, it's showing up on the two monitors on the side. So you can see this band kind of right here. So this is the region where, this is A0, where the clean and noisy Bayes classifier disagree. This, on the right-hand side, this is the relative signal strength plotted as a function of x. And then this red region is the set where it's A kappa, where kappa is 0.4 in this example. So that's the set where the relative signal strength is large and learning is relatively easier. Okay. So we've essentially engineered this definition of relative signal strength so that it's very easy to upper bound the clean excess risk in terms of the noisy excess risk. Right, so if you belong to this class, and you just write out the clean excess risk in terms of this standard formula, in terms of the clean posterior, then you're going to decompose this integral into A kappa and the complement of A kappa. On the first term, you're just going to bound the integrand trivially by 1. And this whole term just gets bounded by epsilon. So this is where the set we're learning is hard, and can't really hope to do much there. But on this other set, A kappa, you can bound eta minus a half in terms of, you can bound it by 1 over kappa times eta tilde minus a half, right? That's just definition of relative signal strength. And now this is bounded by 1 over kappa times the noisy excess risk. So very straightforward. We essentially engineered this definition of relative signal strength so that you could do this. And now this makes it very straightforward to get bounds on, for a given learning algorithm, to get upper bounds on the excess risk, the clean excess risk. So essentially, if you have you can take any learning algorithm that we know how to analyze in a standard learning setting and apply it just on the noisy training data and get an upper bound on this term. And then that's going to translate to an upper bound on the other term. The key point is this term epsilon you can't really get rid of, right? So I'm going to illustrate that in a couple of slides. This is what's going to be an irreducible component of the error. All right, before I do that, let me just say briefly that I've been focusing on the binary setting, but all of this holds in a multi-class setting as well. Let me not go through the details of this slide, but you can generalize everything to multi-class. And this is what the relative signal strength looks like in a multi-class setting. Again, it's not important that we go through the details right now. If the binary case, I think, is sufficient for understanding this. All right, so let me just show you an example of what I'm talking about. All right, so how you can apply a standard learning algorithm, standard analysis, to get an upper bound in this posterior drift setting, for which there's a nearly corresponding, or a corresponding lower bound. All right, so I'm just going to go back to some classical analysis, VC theory and so forth. So suppose F is a set with finite Noetherajan dimension. Noetherajan dimension, if you're not aware, is just a multi-class analog of VC dimension. So I'm going to, if we want to get an upper bound on the learning algorithm, we might need an additional assumption. And here my additional assumption is that the noisy Bayes classifier belongs to this set, capital F. So I'm defining the set pi of epsilon kappa F, which is just my previous assumption. Plus, I'm also going to assume that the noisy Bayes classifier has finite Natarajan dimension. It belongs to this set F. Right, then in this setting, I'm going to talk to you first about an upper bound. Right, so let's just say we have our noisy training data. And let's just consider empirical risk minimization on the noisy training data. Call that algorithm F hat. Then you get this upper bound on the clean excess risk. Right? And this is just straightforward application of what I showed you 2 slides ago. You've got that epsilon term. And then this is an upper bound on the noisy excess risk with a factor of 1 over kappa. Right? So that's just straightforward application of existing analysis of ERM to get that upper bound. But furthermore, there's a lower bound. So now, in this last expression, it's the minimax excess risk. So here we're taking the infimum over. So here F hat ranges over all possible learning rules. And this says that the minimax excess risk is bounded below by this expression. And so you can compare the two, and you see that ERM, just ignorant of the noise, just ERM on the noisy data, it comes very close to this lower bound, right? So they're nearly matching. So this is the end of the theoretical story that I'm going to tell. I mean, you can think of this as an example theorem. You could take other learning algorithms that you like to analyze and plug them in and get similar upper bounds here, and presumably get corresponding lower bounds. And so the take-home message here is that just being ignorant to the noise is it's hard to do much better, if at all.
So just a question, sir. Could you comment a bit on the RSS and how to interpret it? So if does it encompass label noise that is homoscedastic or heteroscedastic, that is depending on the location of X, or?
Yes, absolutely. So yeah, let me just go. Let me go all the way back here. So in these transition probabilities, right? So this can depend on X, the probability of corruption.
Right.
Yeah, and so we're not explicitly using these transition probabilities in our model. But still, we're not imposing any restrictions. So these can be quite general, and so.
I understand, but like how in your bound, like where can we read the variation of the noise across the X domain?
So in the lower bound, there's. Right, we're taking a supremum over this set, and it encompasses all different kinds of posterior drift problems, which will have feature-dependent label corruption. So it just so happens, it's not explicitly shown, but the worst case performance has this little.
I see.
Yeah.
Is the label number?
Yeah, capital K here. This theorem is in the multiclass setting. So capital K is the number of classes. Yes. Yeah. Why? No. So it's you could get the upper bound to match this if you knew the set A0, if you knew where the noisy and clean base classifiers agree. In that case, the optimal strategy isn't quite this. It's do ERM on A0, where there's some transferability potential. Clean and noisy base classifiers agree. And on the complement of that, guess randomly. And that gives you the extra factor of 1 over k by guessing randomly. Of course, we don't want to assume that the set A0 is known. So we have it. So I don't think this can be improved. It's conceivable that this could be raised to match this. Okay, so that's all fine. That's the theory. Is this theory consistent with practice? I mean, I stated I wanted a model for posterior drift that was realistic. So, you know, your first reaction might be, well, this doesn't quite make sense that this would be realistic or consistent with the modern practice. For one, state-of-the-art methods for classification with label noise aren't just doing ERM or some simple method on the noisy data. There's a whole host of, I mean, there's a big literature on this and lots of elaborate methods to try to compensate for noisy labels. For another thing, in deep learning, it's well known that if we just do ERM on the noisy labels, that the performance degrades as the amount of label noise increases. And here's a figure taken from this paper that illustrates this, where the horizontal axis is the percent of corruption in your labels, and this is test error. So both of these suggest that ERM, or just being noise ignorant, doesn't seem to be what people are doing currently. So I'm going to show you some experiments, or actually I'm just going to show you one set of experimental results and describe a very simple algorithm that is consistent with our theoretical message, but also gives state-of-the-art performance on label noise problems. So the setting is there's a data set that's been curated by some people. They took the CIFAR-N and the CIFAR-100 image classification data sets, and they went out and they got some human labelers to assign labels. I think at least three human assigned labels for each image. And so they maintain a website and they have a leaderboard, and you can submit your algorithm and your performance. And so this is really the main benchmark that people use in this literature on label noise. So we looked at that, and our algorithm, and I don't want to try to convey that this is any kind of innovation, but what we did is we took a fixed feature extractor, one that was published last year, Dino V2. This is a foundation model for images that was trained by self-supervised learning using all the latest and greatest techniques and tricks for image data. And we just use that as our feature extractor. And then we fit a logistic regression on those features, training on the noisy data. So in other words, ERM with a linear model and the logistic loss. And we ran it, and it worked surprisingly well. So in this table, first of all, the numbers are accuracy that are shown here. And these are the three leaders on the leaderboard at the time we ran this experiment earlier this year. And if you look at CIFAR-N, the authors came up with 5 different ways of aggregating the human labels to create a noisy label. So that the aggregated human labels are viewed as the noisy label here. And this simple setup, we get an improvement in the state-of-the-art performance on 4 of the 5 ways of aggregating those labels for CIFAR-10. And in CIFAR-100, we also get a substantial improvement in the state-of-the-art performance. Okay, I'm just showing you this one set of experiments, but there's a few other experimental settings that are common in the label noise literature, and we ran it as well and got similar conclusions. So again, I don't want to say that our theory explains all of this. I just want to try to say it's consistent with what we're seeing here, right? Obviously, a big part of the performance is the quality of this feature extractor. And we had the luxury of just downloading it and running it, right? But a lot of work went into that. Yes. No. So most of the competitors, I think they try to extract their own features. Yeah. We did. So at the request of reviewers, we reran some experiments trying to get at that question. What happens if the competitors have access to Dino V2? One thing I can say is, suppose you do what we did, and then you do fine tuning. You update all of the weights in the entire model. That actually makes the performance worse. So somehow, fitting a model in noisy training data, the feature representation suffers from that.
Dino V2 looks at the label data?
No, Dino V2 was trained using unlabeled image data, lots of different benchmark image data sets using self-supervised learning, so no labels.
So I wonder if your results say something about the way the noise has been generated by these humans more than about actually your feature extractor. Does that actually mean that the way that humans have generated noise has actually been somewhat favorable, meaning that in that case your average RSS is actually not so bad?
Yeah, is the average RSS large for human generated noisy labels?
Or it depends on humans, of course, but maybe you had some gentle humans here.
Mm-hmm. Yeah.
Clearly, if you wanted to defeat the algorithm, you could. Mm-hmm. Well, I mean, if somebody had listened to your talk and wanted to change the labels in a way such that your RSS would be actually small or unfavorable, then of course, I imagine.
Sure.
Yes.
Sure. Yeah. Right. Yeah. So it's definitely a point for discussion. How accurate is this model of posterior drift?
With respect to real-world noisy labels. Yeah.
We've looked at other experiments where it's synthetically generated noisy labels. There's some approaches in the literature for doing that, and
We get similar findings. Yes.
So a common kind of simple method for dealing with noisy labels uses soft labels, right? So you kind of not binary targets, but softened versions of those. Mm-hmm. I'm wondering whether you looked at that in your setting. Just you could do the same, V2 Dino V2 features and train with that, mm-hmm. comparatively, and then also if that says how that would match with your RSS measure.
So assuming that at this stage we have access to soft noisy labels.
Exactly.
Okay.
So just do binary, do cross entropy.
So yeah, I guess given that you have multiple annotators per image, you could get a measure of soft You could get a measure of confidence on your noisy labels.
And then do maybe a weighted heuristic regression or something.
Or no, I was thinking something simpler. You could just say that the targets in general are always, instead of 0 or 1, it could be 0.97, 3.
Gotcha. I gotcha. Yeah. No, we didn't try that. Yeah. So, yeah, so that's it. Relative signal strength, a point-wise measure of transferability and posterior drift / label noise problems. And a basis for adapting existing learning theoretic tools to this domain adaptation setting. I illustrated that with a Massar-like condition. We've also got something analogous to the Sibikov condition, and potentially others could be developed. So again, the take-home message is in this, in this perspective, ERM is hard to beat. Thank you.
Questions?
So, yeah, when you were introducing this relative signal strength, you said you wanted a non-parametric series label shift. It seems pretty similar to this distribution shift in the Kai and Wei papers. It needs to have different.
I'm not. Which paper is that?
The Kai and Wei 2021.
Oh. My understanding is in that paper, they assume that the clean and noisy Bayes classifiers agree.
Whoops. Okay, so were they in covariance shift?
No, they're focused on posterior drift. So the P and Q marginals agree. X marginals. And just the posterior changes.
All right, let's thank the speaker again.
Okay, thank you.
We'll take a short break and resume at 11:05.